Welcome to Fossil Fundamentals, a science web series all about fossils. In this episode, we will answering one of the ultimate questions. How do you date fossils? Ever wondered how scientists determine the age of fossils? Fossil dating doesn't simply involve a romantic dinner or having rocky relationships. Scientists actually use different techniques to date fossils. Each technique has their own strengths and limitations. During this episode, we will be going through these main techniques. There are two main methods of dating. These are relative dating and absolute dating. Relative dating is about figuring out whether a fossil is older or younger than other fossils. Absolute dating, as the name suggests, is about providing absolute ages or age ranges. Both methods offer unique insights into Earth's past, from revealing the sequence of life forms that have lived on our planet to helping us understand how life has evolved over billions of years. Chapter 1. Relative dating. Relative dating is a method used by scientists to determine the chronological order of events in Earth's history, without assigning specific ages to the events. It involves comparing the ages of rock layers and the fossils contained within them, using a set of principles and techniques. In this chapter, we will cover some of the key aspects of relative dating. Method 1. Stratigraphy. First up in our exploration of fossil dating methods is stratigraphy. This method is a cornerstone of the science of geology and is based on a principle that is both simple and profound, the law of superposition. This law states that in an undisturbed sequence of sedimentary rocks, the youngest rocks are at the top, while the oldest are at the bottom. It's like a layered cake, where the bottom layer was baked first and each subsequent layer was added on top. Stratigraphy's application in fossil dating comes from the understanding that fossils found in the same layer of sedimentary rock are of a similar age. This helps us establish a relative chronological sequence. For instance, if we find a dinosaur bone in a layer of rock, we can reasonably assume that the bone is as old as that layer. So if we know that the layer above it was laid down 100 million years ago and the layer below it was laid down 105 million years ago, we can conclude that our dinosaur lived sometime in between those periods. Stratigraphy also provides context. It helps us understand the environment in which these organisms lived, the changes that occurred over time, and even events like volcanic eruptions or meteor impacts that might have been responsible for their extinction. Like all scientific methods, stratigraphy has its limitations. It's excellent for establishing a relative timeline, but it doesn't give us precise dates. It tells us that one fossil is older or younger than another, but doesn't tell us by how much. For that, we need to use other dating methods, which we'll explore later in this episode. As we delve deeper into the different methods of fossil dating, remember that stratigraphy is the bedrock upon which many of these methods are built. It has been used by geologists for over 2 centuries and continues to be a fundamental tool in our quest to understand Earth's history. Method 3 and 4. Biostratigraphy and cross-cutting relationships. Here, we explore 2 other relative dating methods. Biostratigraphy is based on a principle that certain types of fossils, known as index fossils, are characteristic of specific geological time periods. Index fossils are unique because they're widespread, easily identifiable, and only existed for short periods of geological time. For instance, trilobites are an index fossil for the Paleozoic era. By identifying the index fossils present in a rock layer, scientists can estimate the age of that layer and the fossils within it. So if you find trilobites in a rock, you know that the rock must have been Paleozoic in age, between 540 to 250 million years ago. You do not find trilobites in Jurassic rock, as Jurassic rock is 200 to 140 million years ago. Cross-cutting relationships is a principle which is quite straightforward. If a geological feature, like a fault or an igneous intrusion, cuts across other layers, it must be younger than the layers it intersects. Think of it like slicing through a layered cake. The knife that cuts through the cake is like a geological event that has disrupted the existing layers. The cake layers were there first, and the knife, or geological event, came after. What does this mean for dating fossils? Fossils found within a layer that have been disrupted by a geological event can provide clues about the relative age of that event. If a fossil is found in a layer that was cut by a fault, for instance, we know that the fossil is older than the fault. These 2 methods, biostratigraphy and cross-cutting relationships, work hand in hand with stratigraphy to paint a more complete picture of the relative ages of fossils. They help to refine and confirm the timeline established by stratigraphy, providing a more nuanced understanding of Earth's history. So the next time you come across a fossil or a rock, remember that they hold secrets of the past, waiting to be unlocked by these fascinating methods. Now, let's shift our focus to absolute dating methods. Absolute dating, also known as numerical dating, is a method used by scientists to determine the specific age of an object, fossil, or geological event. Unlike relative dating, that establishes a sequence of events without assigning specific ages. Absolute dating provides actual numerical ages. Various methods are employed for absolute dating. The choice depends on the type of material being dated and the time frame of interest. One of the first methods is radiometric dating. Radiometric dating is a method that utilizes the natural decay rate of certain isotopes to calculate the age of a material. It's like a clock hidden within the very fabric of an object, ticking away as isotopes transform one into another. This transformation process, known as radioactive decay, is a natural phenomenon that occurs at a predictable rate. Every isotope has a half-life. Half-life is the time it takes for half of the parent isotopes to decay into their stable, daughter isotopes. By measuring the ratio of parent to daughter isotopes, we can calculate the number of half-lives that have passed, and thus, the age. Carbon-14 dating is a classic example. Carbon-14 is a radioactive isotope of carbon that is present in the atmosphere and taken up by living organisms. When an organism dies, it stops taking in new carbon-14, and the existing carbon-14 starts to decay into nitrogen-14. The half-life of carbon-14 is about 5,730 years. So, by measuring the ratio of carbon-14 to nitrogen-14 in a sample, we can determine when the organism died. Carbon-14 dating is effective for dating relatively young fossils, up to about 50,000 years old. Other isotopes, such as uranium-238, are used to measure older rocks. These other isotopes allow us to look even further back in time, beyond the reach of carbon-14, by choosing the appropriate isotope for the material and time frame of interest. Scientists can use radiometric dating to determine the age of fossils and rocks, often with a high degree of accuracy. Next, we delve into some fascinating absolute dating methods: optically stimulated luminescence, electron spin resonance, and thermoluminescence. First, let's talk about optically stimulated luminescence, or OSL for short. This method is a bit like a stopwatch. It measures the amount of trapped electrons in minerals, such as quartz, that were exposed to sunlight or heat. When these minerals are buried and shielded from sunlight, they start accumulating these trapped electrons. By measuring the concentration of these electrons, we can figure out when the sediment was last exposed to sunlight, thus dating the time of burial. This makes OSL particularly useful in archaeological and geological contexts. Electron spin resonance, or ESR, is a method that also focuses on trapped electrons, but in this case it's in tooth enamel, bones, or certain minerals. The trapped electrons are released when the sample is exposed to a magnetic field. By measuring this, we can estimate when the sample was buried and cut off from cosmic radiation. This makes ESR especially valuable for dating fossils, especially those in the range of tens of thousands to a few million years. Finally, we have thermoluminescence, or TL. This is similar to OSL, but it measures the amount of trapped electrons in materials like pottery or burned flint when they are heated. When these materials are heated to high temperatures, the trapped electrons are released, producing light. The intensity of this light can tell us when the material was last heated, providing a date for archaeological artifacts and some geological materials. So, you see, each of these methods allows us to measure the number of trapped electrons in different materials and determine when those materials were last exposed to sunlight or heat. This gives us a more accurate picture of when a fossil or artifact was buried, providing us with absolute dates. These dating methods offer unique insights into the absolute ages of fossils and sediments. As we've seen, dating fossils is a complex task requiring a combination of methods. We've journeyed through the relative dating techniques of stratigraphy, biostratigraphy, and cross-cutting relationships, where the age of fossils is determined in relation to other layers and features. We've also explored the absolute dating methods such as radiometric dating, optically stimulated luminescence, electron spin resonance, and thermoluminescence, which provide a more precise age based on physical and chemical properties. Remember, the choice of method depends on the age range and the type of material being dated. And it's essential to keep in mind that these dating results come with a certain level of uncertainty. That's why scientists often use multiple methods to cross-verify their results, ensuring a more accurate age determination. These methods together help scientists piece together the fascinating puzzle of life's history on Earth. So the next time you see a fossil, remember the intricate science that goes into determining its age. We hope that you enjoyed this episode and now have a better understanding on how scientists and paleontologists determine the age of the fossils that they find. If you enjoyed this episode, please like, subscribe, and leave a comment in the comment section below. Your support is appreciated, and we hope to see you on another episode of Fossil Fundamentals real soon. Keep exploring, keep questioning, and remember that every rock has a story to tell, every fossil a secret to reveal.